What's up? Want to go in? Remember, we got the exam next week. There's a very, very good chance that we are going to, we're going to finish this chapter today, without a doubt. I have two examples, and I think that's really what we want to focus on here. So I'm assuming that you're seeing my OneNote. Okay. So we want to do example 4.5. So let's go do this. So let me sort of like set up here a little bit, and then let's get going. So what we want to do here is that we want to calculate the next circuit. Okay, here's our next example. And this circuit has a twist, and that's really what I want to show you here. So the first thing that we want to do here is that we want to go do their standard stuff. What do I got to do? We see here is that there are dependent sources. So this implies here that the only way we can calculate RTH is that we got to get the ratio of VOCI short circuit. One cannot use method one. If you try to use method one, you're guaranteed to lose half your points. Okay? You're guaranteed to lose half your points at the minimum for the Thevenin circuit on the quiz or the exam. So here we go. So our step one here is that we want to go determine VOC. So let's go determine it. So what am I going to do? I'm going to pull out the load. Okay. So if I'm going to pull out the load, the first thing that I'm going to do here is that I'm going to have this circuit here. So remove load. So if I do that, then my circuit looks like this. I have a dependent source. That looks like this. And then this is a 4 volt. This is an 8 volt. And this is my circuit. So I know that this is A, this is B, which means then this is VOC right there. So my job here is to calculate VOC. So what should I do here? I think the easiest thing, right, probably the most common thing that people are going to do here is that they're going to think node, right? Because you got to calculate voltages. Well, I disagree with that. And one of the things that's real clear here is this guy right here. Check it out. See how this guy has the controlling element is I right here. Actually, let's not put it there. This is the controlling element I. But note, I have a constant source and I have this. So what I can do here is that I could come in here and I could do a KVL loop right here. So if I apply a KVL loop around top loop, we get, check this out. What am I going to get here? I'm going to go left here. Actually, I'm going to go the other direction. I don't want to go that direction. Oh, man. I don't want to go that direction. The direction I want to go is I want to go this direction because I want the plus sign. So here I go. So look at that. I'm going to start at node A. So then I'm going to get plus VOC. I'm going to get plus 8. Because the I direction is defined here, I'm going to assume then that that's going to be minus 2I. And then I'm going to get plus 6I. Look at that. Right? So right away, what I'm seeing here is that I'm getting one equation that tells me what that is right there. So what you're seeing here is that this guy right here has to be VOC, which is then going to be, if I take it to the other side, I'm going to get minus 8. Then I'm going to get minus 4I. However, check this out. There's only one current in this loop right here, and this or the outside branch. You could see that I has to be 4A. So therefore, this is then going to give me minus 8, minus 16, minus 24 volts for VOC. Not everything has to look like a nail. Actually, that's all the way at the edge. So I'm going to bring this into here. And so there we go. I got VOC. Now I'm going to go determine I short circuit here. So the next thing I want to determine I short circuit. So what I'm going to do, I'm going to put a short across the open here. So if I put a short across the open, what do I get here? Well, what I'm going to get here is I'm going to get the following thing. I got to redraw my circuit. How about if I do this? I'm going to copy this. I'm going to put it right in here. So none of this is valid anymore, right? So what I'm going to do here is that now I'm going to come in here and I got to put a short across this here. And that's the direction of I short circuit. Okay, so here I go. So now I place a short across AB. So how should I choose my currents here? Well, I know for a fact here that this guy is 4 amps. Because the outer loop here is I'm going to pick I to be in this direction, the same direction as the 4 amp. So then that really means that there's only one unknown loop here. No, there's two unknown loops, but I'm going to call this IX. So what I'm doing here is that I see that I have 3 loops, one current source. So I have 2 loops, and there's no super loops, but there's loop I and loop IX. But I'm going to choose a solver for I short circuit. So that should give me 3 equations, 3 unknowns. So that means I'm going to have I, IX, I short circuit. So let's go do it. So if I do that, I'm going to start with loop I. So if I look at loop I, what am I seeing here? Well, I see that I have only one resistor in the loop. So I'm going to get 2I. Then I hit that voltage source. I hit a minus sign. So then I take it off to the other side. And then as I come all the way around, I have a minus for this guy here. So I'm going to get minus 6I equals a minus, and then I take it to the other side, I'm going to get 8. So again, right away, in this case, because of the short, that means I could immediately get what I is. So I, in this case, I didn't really think about that, has to be minus 2 amps. Okay, so I have the current. So now let's go to loop IX. So in this case, what am I seeing here? I see one resistor. So I'm going to get 2IX minus 2 times 4 for the mutual. And then I have a series of things here. So I hit the plus. So I'm going to get the minus 8 on the other side. I hit the plus. I'm going to get the minus 4. And you could see here that I have minus 8 here, minus 8 here. So I can immediately cancel those out. So then this tells me here that IX, in this case, is then going to be minus, right? Minus 2. Is that right? Let's make sure. I'm going to get minus 2A for IX. Can that be right? Yeah, I mean, I actually don't even have to calculate that. I really need I short circuit. So then if I go look at my solver, I have I short circuit. Then what I'm seeing here is that I short circuit should be what? Well, you could see here that I short circuit is going like this way. You could see that I goes this way. And then 4 amps goes that way. So you could see here that I short circuit should be 4 minus I. So in this case here, I'm getting 6. I'm going to get 4 minus 2. So I'm going to get positive 6 amps for I short circuit. So I have I short circuit. So then when I look at this thing here, that means I now have my Thevenin resistance. So is then RTH. So I get VOC over I short circuit. So I'm going to get minus 24 volts plus 6 amps. I get minus 4 ohms for the Thevenin resistance. Yes, this is a negative Thevenin oh God, how do you spell Thevenin again? It is correct. You have a negative Thevenin resistance. So if I look at this whole circuit here, okay, and if I was to redraw this whole circuit, I'm going to do the following thing here. Let me see if I can do this. Let me see if I still have it in my thing here. Here's my Thevenin resistance here. So when I look at my circuit here, what do I see here? I can replace this circuit here with my load resistor here, right? Here's my load resistance. And this guy's going to be our load in this case was 2 ohms. I could then come in and replace the circuit with the source that reads minus 24 volts. This is going to be minus 4 ohms. And this is my load resistor of 2 ohms. So I cannot ignore that negative sign here. And so what I want to do then is that the goal here was to calculate what is the current through the load. In other words, we're trying to actually solve for this current I of the load. And when you look at this thing, I'm going to use Ohm's law. You're going to see here that the current of the 2 ohm, which is the current of the load, is then going to be what? It's going to be, of course, it's got to be VOC over RTH plus the 2 ohm. But in this case here, you could see that it's minus 24 over minus 4 plus 2. So I am getting a 12 amp current through that load right there. Now, does it make sense that I really do a current like this? So check it out. Let me show you what's actually happening. Well, one, note that the current, this is node A right here. This is node B. The fact that I got positive, right? That this is positive implies current goes from A to B. So let's go do this. So what I did here is that I went in and I p-spiced this. So let me show you my p-spice. Here's the p-spice, and what you're seeing here is that if I look at that current here, look what you're seeing here. p-spice is telling you that it looks that the current is exactly entering the circuit as we expected. Right, so I'm coming in here with p-spice, and you can see here that the current is legit right there. So I am seeing a current through the load going like this right here, as expected. And you could see that that's 12 amps. So that negative resistance is a real thing here, right? It's totally a real thing. It's not some arbitrary thing that I'm just kind of calculating. And so what I want to do here is that I want to go back and I want to talk about this negative resistance term here. So let's go in and start thinking about this in a legit way. So here we go. This is going to be the interpretation of the negative Thevenin resistance. So this is a DC circuit, no doubt. However, Thevenin circuits can have negative effective resistance. And what I mean by that here is that when you have a dependent source in the circuit, what you find here is that you can have an effective negative resistance, right? This cannot be measured with an ohm meter, right? It cannot be measured with an ohm meter. You would not get a negative resistance value. And what you're finding here is that this negative effective resistance is, so this is closely related to resonance in AC circuits. In fact, this phrase here is known as impedance matching. Oops. Okay, it's known as impedance matching. So what you find here is that if you have AC, what this really means here is that you could think of sine waves and resonant circuits. And the example that I'd like to use in physics 4A here is that of an oscillator. Okay, as an analogy, I know that if you took physics 4B last semester, I know you didn't get to this because I know you guys didn't cover AC. So there's no way you talked about resonant circuits. And we may not even get to resonant circuits if we don't get those goddamn function generators / oscilloscopes. And so here's what happens here. And the analogy here is that let's think about a spring mass system. And what I imagine in a spring mass system here is that imagine that you have a cart. And this cart here is attached to 2 springs. And what you can do here is that you could take this cart and you can displace it from the equilibrium. So what I'm doing here is that I'm going to displace it. And so what happens is that the cart oscillates at its natural frequency. And in this case, I'm going to call the natural frequency omega naught. So what I'm going to do now is I'm going to do a very similar thing here, but I'm going to modify this thing here. And the way I modify this thing is that I take my card again, and what I'm going to do this time is that I'm going to attach it to an oscillator. And what you'll find here is that the way I set this up in campus here is that this arm here now oscillates in a circle. Now the arm, so this is an oscillating arm. The oscillating arm, what you find here is that it has a driving frequency, which I'm going to call MD for driving. And so what happens here is that you can get a resonant situation. You know, let's not talk that way. So if one writes out the differential equation and solves it, one gets that the amplitude is frequency dependent, and it looks like this here. It says that the drive-in frequency minus the natural frequency, and then you have a constant term. this constant is really associated with damping in the system. Now, there's another constant up here, but we don't care about that constant. And what you're finding here is that in the limit, so if you were to plot this thing, in other words, if you were to plot the driving frequency versus the amplitude, you would see that this thing actually resonates at omega naught. So what you're seeing here is that when you're oscillating this guy, you're going to get maximum amplitude at when omega d is equal to omega naught. And so you get maximum amplitude. So the same thing happens with the negative Thevenin resistance. If you have an AC circuit and you resonate the circuit, effectively, you're going to get maximum amplitude. In this case, you'll get maximum current. So let me give you an example here. So check this out. So now, back to the Thevenin circuit. Now you would think that if I take my Thevenin circuit over here, which I'm going to take and bring down with me, and this time what I'm going to do here is that I'm just going to call that R load. You would think that you would have max current if R load is equal to 0. Not true. Because if you calculate the load current now, what you're going to see here is that you're going to get what? Minus 24 minus 4 plus 0, you're going to get minus 6 amps. So you could see that the current is going in the opposite direction. So if I was to come in here in PSpice, change that to 0, and then run it again, look what I get. Oh, come on, PSpice. PSpice is not liking me. Apparently, you can't set resistance to equal to 0, but I can do this, right? I should be able to do. Now let me see if it allows me to run it. Oh, baby, I don't believe PSpice. Oh, it's a positive current, not a negative current. Oh, damn it. So if I come in here, what you're seeing here is that look at the current. So PSpice does not like 0, but I did something very, very small. Of course, this is a positive, even though I drew a negative, and you could see that I'm getting 6 amps going in that direction. The previous circuit was 12 amps in the same direction. However, when one does impedance matching, okay? So when one does impedance matching, what you're finding here you're essentially what? You're resonating a DC circuit in a way. In other words, what we're doing here is that we're going to set our load to 4 ohms. And what you're seeing here is that now you're seeing that in the limit, as our load goes to 4 ohm, you're going to see that the load current now, right, in this limit, you're seeing here that I'm getting -4 plus our load minus 24. And you could see that this thing approaches infinity. And the question is, what really happens here? What you're seeing here is that when I look at my Thevenin circuit, this being 4 ohms, this being -4 ohms, this is effectively doing what? You're creating a short. So when I'm looking at I load, you're then getting maximum current from the power supply. Of course, no power supply in the world can put out max current. So what typically happens is that real power supplies max out their current value. So when you're looking at this scenario here, let's go in and let's look at what happens in PSpice. So check this out. So I'm going to go back into here. And what I'm going to do here is that, look what happens here. So if I pick 3 ohms is that, I'm approaching 4, and then I rerun it, look at the current. It's now 24 amps. Now, if I come in here and I change it again, and let's say I go to 3.75, look how the current starts to increase. So if I run that again, look at that, 96 amps. And then if I do the ultimate and go 3.99, we should have a big ass value in the current. And look at that. Look at that, right? 2,400 amps. And as I get closer and closer and closer to this thing, it's going to start to approach infinity. Of course, if I put 4 in here, PSpice is going to say there's an error, because you can't define an infinite number, because it's right, it's not a real thing, it's a concept. So you're seeing here that in this situation that you're getting these mega, currents here. And if you go and you look at this thing, maybe we go in and we calculate the power. Dude, look at the power, right? 23 megawatts across that resistor. What resistor is going to take 3 megawatts of power being dissipated? It can't. It's not possible. And so what you're seeing here is that that's the effect of the Thevenin resistance here, right? That's the effect. And so if I just to paste this in, you could see here that at 3.99 ohms, I get this massive 2,400, right? 2,400 amps across that 4 ohm resistor, or 3.99 ohm resistor, which is pretty phenomenal. I think that's such a beautiful concept. Again, it's really about AC circuits. This is just a residual in a DC circuit. And one of the things that I'm trying to do here is that I'm actually trying to devise the circuit in case we don't get AC. All the scope stuff, I'm going to have to do this here. Okay, let's go to the last topic of this chapter, and we want to talk about maximum power theorem. So the maximum power theorem, power transfer theorem, what it does here is that it essentially tells us the maximum amount of power that can be delivered to an element. This theorem tells us about the maximum power delivered to a load. It doesn't have to be a resistor, okay? But most of the time, what you're finding here is that a resistive element, you're going to see here is you get maximum power to a resistive load is when the Thevenin resistance and the load resistor are exactly the same. So what we want to do here is that we want to derive this. So to derive the maximum power to a load resistor in a Thevenin circuit here, we imagine that we have this circuit. And there's the load right there. So clearly, if I want maximum power, then I have to take the power with respect to the load and set that equal to 0. Then we get the critical point, and then we sub into the power function. So let's go do that. So if I do that, this is a fairly simple calculation, but it'll be quick here. And here's what we know here. So if I'm talking about, so we can clearly see here that we can calculate the voltage across the load. And what we'll do here is that we'll use VDR to get V of the load. So V of the load, of course, has to be our load divided by the sum of these guys right here times VTH. So now that I have that, then I know that the power of the load should be the load squared divided by R of the load. So now what I want to do here is that I want to take the derivative of this thing here. So if I take the derivative of the power of the load with respect to the load, and of course that's got to be equal to 0, then note that when I look at this voltage of the load, note that the R load is a constant, right? So I'm going to pull this constant out. So I got R load. Now note, oh, wait, we're taking the derivative with the load. I'm going to take, this is the term I'm going to take out. I'm going to take VTH, that's a constant. So then this becomes VTH squared. And now I'm taking the derivative of the load. And you're going to see here that I have that load right there. So I'm going to have R load. Then I'm going to have this term squared times this guy squared. And so clearly, because this is equal to 0, we don't care about a constant. So what I'm really interested in here is that when I start to take the derivative of this guy here, what am I getting here? Well, for starters here, I'm really taking the derivative of a single power on top, divided by that guy. So this is the guy I really want to do. Now, I'm probably going to get the quotient rule wrong, but that's okay because it's equal to 0, so it doesn't matter the order in what I do it in. And so when I look at this guy, what am I seeing here? So I'm seeing 0 must then equal this guy here. So if I use the quotient rule, I'm going to take the derivative of the top, which is 1, times the derivative of the bottom, which should then give me what? Should give me RTH plus R load squared. And I think I'm doing this right. And then I'm going to get what? Minus the derivative of the bottom times the derivative of the inside, which should give me 1. Ooh, let me do this a little bit cleaner. And then I have to take the bottom and I have to square that. And you could see that one of these terms is going to cancel out with this guy. Let me make sure I get this right. Right, I got R load of 1 times that. I think I have a mistake someplace.
Are you missing an R load on the second term? Because you didn't take a derivative of R load.
Oh, shoot. I forgot about the second term right here. Thank you. Okay, so if I do that, then now we only care about the numerator. So if I only care about the numerator, you could see that this guy's going to be RTH plus R load minus 2 times the load. And that's equal to 0, which tells you that RTH must be R of the load. So this is the critical point. So the critical point is this guy. So this is the critical point of when the load gets maximum power. Okay, when it gets maximum power. That's the maximum power theorem right there. I mean, it's just a fairly straightforward calculation here. And so what I want to do here is that let me set up here and I'm going to let me go get the last example. Where is that last example? And here it is right here. So this circuit then, what we're asked to do is we're asked to do what? We want to calculate the maximum load or the maximum power to the load circuit here. So what do I got to do? That means here we know that maximum power occurs when RL equals to RTH. So that's what we got to do. We got to go calculate that. Note dependent sources. Dependent sources implies what? The only way to calculate RTH is this way. So let's go do it. So the first thing that I'm going to do here is that I'm going to go get my that circuit here. And I think I'm going to do this right here to try to save time. And what I'm going to do here is that I'm going to do the following thing. So let me just set up here real quick. Sorry for the delay. As much time as I think that I'm prepared, apparently I'm lacking today. So what we're going to do here is that we want to determine VOC. So let's go look at that. So here I go. So here's the circuit here. If I want to go determine this guy here, what do I got to do? Well, what you're seeing here is that I got to define my A and I got to define my B. Okay. How am I going to solve for this circuit here? Where would I put my ground at? Well, I know that this guy has to be VOC right here. I know that I have two voltage sources. I think I would put my ground right here. The only reason why I'm putting my ground is that now I can go in and I can define this node right here, VOC. That way I don't have to think about how to do this thing. Now, the thing that's interesting is that note that that 9 amp is in series with the 2 ohm resistor. So I immediately know what Vy is. Okay. So the fact that 9 amp and 2 ohm are in series, this immediately implies that Vy, which is 2 times 9, is then 18 volts. So that means I'm not going to choose. I now know that that's 18 volts. So that means here that my current controlled voltage source, 2Vy, is now going to be a value of what? 2 times 18. So it's going to be 36 amps. So I do not consider that current source to be a dependent one. I would literally come in here and I would scratch this guy out and I would write 36 amps for that source right there. So that is not a dependent source anymore. It's a ordinary current source. So when I start to do this, then I'm going to start to look at my nodes here. And the first thing that I'm going to look at is that, let me go and I'll look at this. So I'm looking at this. So this, here's a node right here. Ooh, I don't like that red. So let me change the color here. I'm going to go to green. So you could see that this node right here is a known node, right? This is 3ix. And then if I look at the other node, you could see that this voltage source is not connected to the ground. So this has to form a supernode. So what's a good labeling scheme? Well, why not V1 and V2? So it looks to me like I only have, right? I have the VOC node. So if I count here, there's the ground. I know the green. So I only have the red and the blue node. So I could see here that I have what? I have 3 nodes. right? I have 1, 2, 3. Let's do it right. So no Carlos shortcuts. So I got 1, 2, 3, 4 nodes. I have 4 nodes. I have 2 sources. So I have 2 node equations. So the question is, what do I know about these nodes? One is not connected to the ground. So that means this guy here is my supernode. So I have a supernode. So that tells me I have a supernode between 1 and 2. So therefore I have a supercondition between 1 and 2. And then I have the other node, which is VOC. So then I have node VOC. And then I need a DC for IX. And I think that's it, right? Let me double check here. So this means I have 4 equations, 4 unknowns. So my matrix should be V1, V2, VOC, IX. So let's go set that up. So here I go. So I'm going to start with supernode 1, 2. So if I look at supernode 1, 2, I'm going to start with 1. I could see that there's only 1 resistor. So I'm going to get what? I'm going to get 1/2 V1. Then I have a mutual, which will be 1/2 3IX. Then I go to node 2, right? So this is node 1. Now I'm going to go to node 2. So I have 2 resistors, which will be 1/2 plus 1 connected to 2. Then I have 1 mutual with what? I have 1 mutual with VOC, and then I have 1 mutual with 3IX. And then do I have any current sources flowing in or out of the supernode? I see 9 coming in, and I see 36 going out. So it should be equal to 9 minus 36. And so here is node 2. So then I'm going to look at my supercondition between 1 and 2. I see that the 2 is the high. So then I'm going to get V2 minus V1 equals 2 volts. And then I have my node for VOC. My node for VOC in this case is going to be, I see that there's only 1 resistor. So I'm going to get 1/2 VOC. Then I have 1/2 V2. And then I have a current flowing out of the node, which will give me -9. And then finally, I'm looking for my DCIX. And I could see that my IX is flowing through the 2 ohm resistor. So it should be V1 minus 3IX equals IX. So in this case here, it should be V1 minus 3IX, and then it's going to be 2IX. So of course, if I clean this up just a little bit to put it into matrix form, it's going to be 3IX. Nope, my bad. It's going to be 5IX equals to 0. So now I have my matrix. Okay, so if I go put it into matrix form, that means then I'm going to set up V1, V2, VOC, IX, and then of course my constants. And then if I go do my standard thing that I do, I have 1 here, there, not there, but here. So if I look at that 4, I'm going to go and I'm going to get 1/2 minus 1, 0, and then 1. So if I go focus on 2, I got it here, here, here. So then if I go put that in there, I have 1/2 plus 1, 1 minus 1/2, 0. Now I'm going to go after VOC. And it looks like it's only in 2 spots. So then I'm going to get 1/2, 0, 1/2, 0. And then IX. So if I look at IX, I got it here. I got it there. And I got it here. So if I go do that, let's be careful here. So I got minus 1/2, minus 1. So I'm going to get 1/2 plus 1. Let's make sure that's right. That looks right. I got 0, 0, and then finally minus 5.
That
So
first
I have
IX term
B1.
is 3 halves.
Yes. Say that again.
Is that first IX term not 3 halves?
Yes, it is. Thank you. And then this is IX. Now let's look at my constants. So this should be 9 minus 36, 2, right? I should have been doing this here. Here's my constants. So then if I start to put those in, I get minus 9 and I get 0. So if I look at the solution to this, using matrix magic, I get VOC is minus 79.3 volts. So I now have VOC. So the big difference here now is that I got to do what? I need to come in and replace this with a short to go get I short circuit. So let me go and do this. So now my job here is to go calculate, where's my mouse at? Damn it. It's somewhere. Here it is. So now I want to go determine I short circuit. So here I go. So I'm going to come in, I'm going to paste my circuit. And this is my circuit right here. So that means here I need my current to be going from A to B. It's going to be going in that direction. That's I short circuit here. So if I look at this guy here, I'm going to do the counting and start to look at this thing. I don't see any reductions here. So I clearly have 4 loops. How many current sources do I have? I have 2 current sources. So that means here I have 2 loops. Now the question is, what kind of loops do I have? Well, I can see here that one of these loops is this guy right here. It's a super loop. And note that this is a problem that we did in lecture here. But this is different because the other problem had a resistor here. This is a short here. And which direction am I going to choose? I'm going to choose it in the direction of IX. So right away, I could see here that I'm going to pick IX to be here. And then if I pick the exact same thing as I did before, I think this was my choice before. And then I have this other loop right here. And I'm going to pick it, of course, the same direction. So therefore, I'm going to pick this guy to be I2 in that direction right there. So now those are my two loops here. So what do I know here? Well, one is a super loop between 1, 3, and x. So that means I have two super conditions, 1 and 3, and 3 and x. Okay, that deals with the super loop right there. Now, then I have a regular loop. So I got loop 2. Then I ask, how many DCs are there? Well, there's the DC for IX, but that doesn't count anymore because I defined my loop current to be IX. So that doesn't, I don't have to define that. The other dependent condition here has to be VY. So I have one DC and I want to solve for I short circuit. So I should have a solver for I short circuit here. So that's what we want to look at here. So let's go do that. So if I do that, let's count here. So I have 1, 2, 3, 4, 5, 6. So I have 6 equations and I have 6 unknowns. What are my unknowns? I have I1, I2, I3, IX, I short, let's do VY, and I short circuit, right? 2, 4, 6 variables. Okay, let's go matrix this guy up. Let's go write this guy up here. So here I go. I'm going to start with the super loop. So I have super loop between 1, 3, and x. So let's do that. So if I look at loop 1, I'm going to have what? I'm going to have 2I1 minus 2I2 plus loop 3. Look at that. 0 for loop 3. No resistors there. And then I have loop IX here. I see that there's only one resistor, so I have 2IX, but note, no mutual resistors. So that's pretty damn fast right there. So now, let's make sure that I have that right. And so now I'm going to look at my sources. So here I go. I started over here with the resistor V, 2 that's labeled VY. So if I go around, look what I'm going to do. So typically I put my equal sign further out. So here I go, a constant source, I hit a plus, I take it to the other side. So I got -2. I'm coming all the way around. Look at this, I hit the positive 3IX, but because that's a voltage source that's dependent, I want to keep it on this side. So I write 3IX. And then I keep going all the way around, I'm done. Now let's go after the super condition between 1 and 3. So if I look at 1 and 3, you could see that the 3 is going with the 9. So it should be I3, I1 equals 9. Let's go to the super condition between 3 and x. And if you look at that, that's a dependent one. So remember, you want to write it into matrix form. So look at 3 is in the direction of Vy. So it's going to be I3 minus Ix, and then it would be equal to 2 Vy, but I want to bring it to the minus sign, so it should be 2 Vy equals to 0. So then I'm going after loop 2 now. So if I look at loop 2, I see I have 2 resistors. So I'm going to get 1 plus 2. And then I have a mutual with loop 1. So it's got to be 2I1. And then what about sources here? There's one source. So note that that's a negative, but because that's a dependent, I write it on this side. And I get 3Ix equals to 0. Now I want to go after Vy. So my DC here, you can see, is between loops 1 and 2. So let's write that. So my DC for Vy is then going to be, look at the current here. 2 is in the positive, 1 is in the negative. So therefore, I'm going to get 2I2 minus 2I1 equals Vy. But Vy, we want it in matrix form, so I'm going to bring it to this side. So that's got to be equal to 0. And then I want my solver for I short circuit. And if I have my solver for I short circuit, you can see here that it's the difference between loop 2 and 3. So therefore, 2 goes in the direction of I short circuit. So it should be I2, I3 minus I short circuit equals to 0. So now what I need to do here is that I need to go in and matrix this guy up. So let's go set this up here. So what am I seeing here? So I have I1, I2, I3. How did I label these guys? It doesn't really matter. IX, I short circuit, Vy, and then I have my constants. So here I go. 1, 1, 1, 1. So then I start writing them in. I get 2 minus 1, 0 minus 2. Let me make sure I have minus 2, 0. Now I'm going to go after I2. I2 should be here, here, there, and there. So then I go minus 2, 0, 0, 1 plus 2, and then I get 2 and 1. Now I'm going to go after the next. So the next one is 3. So I get 3 here and there. So I'm going to see here is that the first one gives me 0, 0, 0, and then I'm going to get 1, 2, 3, and then I should have, am I messing up here? Let's see, 0. I did mess up. So this is 1, 1, and then I get 0, and then I get 0 again, and then I get minus 1. So now I'm going to go after IX. IX is here, here, there, and that's it. So I know I got zeros. So let's do this. So I have 2 plus 3. So I'm going to write 2 plus 3. Then I have 0. The next one is minus 1. The next one is minus 3. And then I get 0 and 0. So I short circuit should be very fast because it should only be in the last equation. So you could see that that's got to be minus 1. So this is it for this guy right here. So then finally, I'm just going to go 0. Oops, wrong color. I'm going to go 1, 2, 3, 4, 5, minus 1. Vy is the next one. So when I look at Vy, I'm getting right there and right there. So there's only 2 places where Vy is at. So they're mostly zeros. So I should get 1, 2 zeros. Then I get minus 2, 0, and then finally minus 1 and 0. So now I have my matrix. Last thing to do here is to look at the constants. And you could see here that this is going to be minus 2, 9, 0, 0, 0, 0. So then I'm going to go get the solution. So if I do the solution here, I'm going to find that I short circuit is then going to be minus 7.67 amps. That's what the matrix solution gives me. So then this tells me here that I have the Thevenin equivalent circuit now. In other words, I know that RTH has to be VOC I short circuit. This is minus 79.3 volts. This is minus 77.67 amps. So this gives me a positive Thevenin resistance that looks like this. In other words, I know that my circuit then looks like this here. Which is 10.3 ohms. And so now I have my load here and I want maximum power to that load. We know that maximum power is when the R load now is equal to 10.3 ohms. In other words, using the power of that, well, I know that the voltage here has to be divided in half. So what do I know here? I know that this has to be 79.3 divided by 2 volts squared, divide that by 10.3, and I get a positive 153 watts for the maximum of the load. And that's the power of the load. So I am officially done with this chapter. Okay. I am officially done with this chapter. When is the exam? Next Wednesday. On Monday, I'm going to give you a quiz on Thevenins. What am I going to do on Wednesday? I'm marching right into the next chapter 5. I was hoping that I would touch on chapter 5 a little bit because tomorrow we start the op-amp lab, which is a DC lab on voltage-controlled voltage sources. And it's a great lab. I really, really like this lab. What you're going to find here is that this lab, the first 2 parts of the lab are probably going to take you 2.5 hours to do. And then there's going to be 2 more parts, and it will probably take you 15 minutes to do. This is more of a wiring lab. The calculations for this lab are trivial. This is a wiring lab. And you're going to see that we're going to be using potentiometers with negative and positive 15 volts. So again, you're going to see that these voltage sources are going to really cause grief for some people. Okay, you got to remember, I'm going to keep up in the ante here with the wiring as much as I can. So I think I'm going to stop because I just have a few minutes left before I go into the next chapter. But the next chapter is an awesome chapter again. Really, really cool stuff here. So, okay. So I want to say here is that thanks for showing up. I'll be around tomorrow in PLC hours and office hours. If you have questions, please stop by. I'd love to hang out with you and chat circuits here, especially that negative resistance, which has to be confounding to many of you because it was brutal when I first saw it. I went like, this is bullshit. But you can wire it though. And I'm actually trying, in case the stuff doesn't come in, I will, I'm actually starting to try to design that lab right now. Hopefully I can finish it because I still have to buy the parts. So hopefully we don't have to order them from China right now. Right, by the way, I've ordered lots of stuff from China that came in right on time. So it's not about China. I think it's just a residue of what's going on in the world. Okay, I'll talk to you guys later, okay?
Have a good one, Carlos.
Carlos.